In this class, we are going to talk about convective fluid dynamics in microchannels. Now, we all know that when we have flow through any normal size channels, the flow may be laminar, turbulent or in between. Now, in microchannels, because of the predominance of viscous forces, the flow can remain laminar for quite some time, and it is also not possible in most of the cases to have turbulent flow in such small devices. So, in other words, in order to obtain or in order to attain turbulent flow in microchannels, one has to sacrifice a huge amount of pressure drop. So, most of the cases we will encounter laminar flow in microchannels. But there will be situations in which the flow at times or at certain pockets may become turbulent, or the mixing will become much more. For example, if there are bends in the pipeline, or if there are internals which are present in the path of the microchannels or in the path of the fluid, or there are entry and exit, then it may lead to near turbulent situation, especially near the corners. Now, this fact has been used to devise mixers at micro scale. Now, we all understand that if we have two fluids which are flowing side by side, then mixing them in a microchannel where the flow is predominantly laminar could be a problem. So, one alternative could be to use these bends intelligently such that they themselves will act as mixers. But we also have to understand that once this mixing pattern sets in, the flow will become stabilized once we are away from that bend. So, we need to have some specific studies in which we can quantify or we can study at depth how the flow becomes turbulent, or how the flow becomes irregular, not straight streamline laminar flow near a 90-degree bend, and how it stabilizes at a certain length from the bend. So, we are going to concentrate today on flow in microchannels, which are generally regarded as straight laminar flow, but in straight channels the flow remains laminar below a Reynolds number of 2300. Though we start to see disturbances with wavy streamlines that may appear even lower Reynolds number, and there is obviously a range of a Reynolds number beyond 2300 for which we may expect truly turbulent flow. Now, as I was telling you before, the straight streamline or straight laminar flow changes when the fluid flows through curves, bends or around obstacles. Now, what happens at the bends is that the centrifugal forces at bends pushes the fluid away from the bend. So, there will be alternatively positions of low pressure and high pressure at different positions at the bend, and this would give rise to mixing near the bends. So, at the wall, the fluid is forced either upwards or downwards, producing a symmetric double vortex which fills the entire channel. Now, this vortex will soon die down depending on the viscosity of the fluid and the dimension of the channel, and may give rise to straight streamline flow once again. So, in order to quantify the flow regime in curved channel elements, we often bring in a number which is known as the Dean number, and the Dean number is Reynolds number multiplied by d by RC to the power half. So, this d is the diameter or the diameter of the channel, and RC is the radius of curvature is the radius of curvature for the bend. Now, this flow regime in curved elements are often called Dean flow, and it's the viscous wall friction which acts against the centrifugal forces present in those bends, and they will bring order to the system. So depending on the value of the DIN number, we can classify the flow at curved bends under several different distinct regimes, and the flow pattern in each of these systems has been probed, and depending on the values of DIN number, we could see rapid mixing between two liquids which are flowing side by side and suddenly come across a T junction or a 90-degree bend, and I will give you examples of that in my subsequent slides. So now let's say we move to a situation in which there is a 90-degree bend, and at this 90-degree bend, what we see is that the straight streamline of the flow before the bend suddenly get mixed in this region, and then afterwards, once we go far from the bend, then the flow becomes stabilized again. So here is the case where viscous forces are important, and in this case the centrifugal forces would try to push the liquid towards this side, and the viscous forces will oppose the centrifugal force and will try to bring order over here. So if we can see that over here there would be if we could measure the pressure at every point, one can see that the pressure from here would be definitely have to be higher than the pressure at this point, so that the flow can take place, and from here to this point the pressure may vary in an erratic fashion depending on whether we are measuring the pressure over here or we are measuring the pressure at this point. Beyond a certain length from the bend, the pressure again becomes similar to what we have before the bend. So these two pressure differences will behave in a similar fashion, and the pressure gradient one can expect from this point to this point and beyond this region will be straight line, will be linear in nature. So what we have shown here is the plot of pressure against channel length, and if we think of this as the 90-degree bend, what we have shown over here, then the pressure will linearly fall between this point and the beginning of the bend, and beyond this line the pressure will again fall linearly. But if we think conceptually what is happening at the bend, at this point the pressure is going to be more, and at this point the pressure is going to be less. So across this there is going to be a pressure jump near the wall where the liquid is, where the fluid is coming, hitting the wall, changing its direction and moving in another direction, and over here where a low pressure region is going to form. So what we see here is a pressure jump near the outer wall and a reduced pressure near the inner wall. So this kind of pressure behavior is quite common even for laminar flow in a 90-degree bend. So this concept that change in flow direction is causing the straight streamlines of the flow to deviate from the straight path can be utilized in a number of devices, and one such device is a mixer utilizing a 90-degree bend. Now what we can summarize our observation is that the investigated flow regimes are laminar with formation of vortex, and we may not see any onset of turbulence in the bends, and at the inlet channel we have an uniform pressure distribution in the cross section, and due to the curvature of the bend the flow is altered in a new direction, and as I said, at the outer side of the bend the pressure is increased compared to the inner side, and this difference in pressure at the curved bend can create mixing due to the presence of the 90-degree bend, and which has further usage in flow in microchannels. It has been shown that approximately 100 micron behind the bend a uniform pressure gradient, pressure re-establishes in the cross section. So, at this point the vortices are already dampened by the presence of viscous forces, and the straight laminar flow reappears and will continue till it encounters another bend in the path. So, the pressure loss in the bend results in vortex formation and is the basis for further calculation in mixing theory. So, we may get more mixing, but definitely at the cost of increased pressure gradient in the path of the flow. Now, we can also look at the fluid dynamics in T junctions, but we'll come to that later on. Let's just think of how 90-degree bend works, and this is some experiment which has been done with two different fluids. So, I have fluid 1 which is flowing and fluid 2, and the volumetric flow of these two are the same. So, the fluids are clearly separated, and then it has a 90-degree bend in its path. So, what would happen is that the pressure gradient up to this point will be linear, and over here there is going to be a high pressure zone and a low pressure zone that would cause the fluid to move from one side to the other, and therefore, the green fluid and the red fluid will mix, and they will mix further, and over here at the exit from the 90-degree bend we are going to get a mixing band which will propagate as we move along this, and very good mixing can be obtained utilizing a 90-degree bend in a microchannel, and that is one of the principal ways to mix two fluids at the microscale, because we know that in a very how to mix two fluids in the bulk, but how do we mix two fluids which are at microscale, and when they are flowing side by side. So, when they are flowing side by side in a microchannel, the only way these two fluids can mix is by diffusion, which we know is inherently a very slow process. So, in order to speed up the diffusion process, in order to speed up the mixing in between the two, purposefully a bend is placed in its path so that we get very good mixing. Now, this has been used, this has been studied for the mixing of different protein solutions, and in T bends this mixing pattern, the study of this mixing pattern gives very interesting results and the results have been correlated in terms of mixing parameters and in terms of the DIN number of the flow. So, I will show you a simple experimental setup in which two protein solutions are flowing side by side, and suddenly when it comes to a T bend, the two protein solutions which are flowing side by side suddenly starts mixing, and it may so happen that they will mix. It may so happen that they are going to overlap, and it has also been shown that for very large values of DIN number, the flow may go from one side and the other flow will go to the other side. So, that the flow reversals, that is the fluid which was flowing from the left, it is going to move to the right, and the other fluid is going to move to the left. So, there are different kinds of mixing which are possible, which can be seen in many such situations. So, the fluid dynamics in T junctions with symmetric inlet conditions, they are like this. So, we have a T junction in which we have liquid 1 which is flowing in this direction and liquid 2 which is flowing in the other direction. If the flow is very small, then we will still have one that is moving from right to left, and the two which will move in the other direction with very little mixing in between the two. And this happens, the classification of the flow patterns, these are 1:1 mixture of two fluids, and the CFD simulations and visualizations simply tells us that for Reynolds number less than 10 and D number less than 10, where D number is defined as Reynolds times D by RC to the power half. So this simply tells us that when both are of the same order, then D is roughly equal to RC, and if this condition is satisfied, then we have straight streamline flow even after the mixing. So the diffusion dominates mass transfer in this case. So this is a diffusion only process, and you get very little physical mixing in between the two. Now when we move to a situation where the D number is where the Reynolds number is greater than 10, but it's less than roughly about 150 or so, but the D number is greater than 10, then we get symmetric vortex. Symmetric vortex are formed, and what you would see is that if this is the boundary 1 and 2, and then I have the T junction, then you are going to get some sort of mixing in between the two, and part of one may go in this direction, a small amount of 2 may come in to the other direction. So the straight streamline flow which was present before, straight streamline flow gets disturbed, and this disturbance is due to the centrifugal force. As I said, D number is defined as Reynolds into D by RC. Okay. So for sharp bends, what you would get is the centrifugal force will start to cause mixing, some sort of mixing at the mixing channel. Now the situation becomes even more interesting when the Reynolds number is greater than 150 and less than about 250 or so. Then this region is called, this is called the engulfment flow. And in the engulfment flow, what you would see is that the symmetry totally breaks up, and the part of the fluid is going to move in the opposite direction, and this one too is going to come in the reverse direction. So the fluid swaps to the opposite side, and this leads to short diffusion length and very high mixing quality. So the mixing increases in such systems. For 200 Reynolds number greater than 250 but less than 400, then the situation becomes even more chaotic, and the two will not come to this side on a continuous basis, or the liquid one will not move into this direction. Rather, we have periodic flows, periodic pulsations of liquid column from one side to the other. Okay. So this pulsating flow has very high, very good quality mixing, and if the Reynolds number is greater than 500, then what we have is a complete mixing of these two liquids. So for Reynolds number greater than 500, it becomes chaotic pulsating flow. The vortex breaks down, and you get the single flashes of fluid swaps to the other side. So the liquid 2 will move to this side, liquid 1 will move to the other side, and this takes place at such a high pulsation that the mixing quality may actually decrease mixing quality may actually decrease. So, depending on the value of Reynolds number and depending on the value of the DIN number, one would be able to classify these type of flows into different specific domains. Generally, with increase in Reynolds number, the mixing quality increases, but that increase does not continue indefinitely. At some point of time, the engulfment of one flow to the other has a periodic nature in it, and as a result the mixing quality may decrease. But we have to keep in mind is that these are CFD simulations, these are highly specific to the geometry of the system as well as the nature of the fluid in question. So, the limits of Reynolds number and DIN number that I have proposed so far is system specific, and one has to be careful in conducting these numerical studies before one can design an actual mixer based on these phenomena where centrifugal forces help in the mixing and the viscous forces will try to reduce any or to try to suppress any vortex formation. So, these are interesting areas of research where one can think of use these simple concepts to the design of micro mixers. Okay. Next we are going to, as I was mentioning about the different ranges of Reynolds number. So, for example, Reynolds number higher than 1000 are usually avoided in T-shaped micro mixers, as it leads to very high pressure losses, and that kind of pressure loss cannot be sustained in most of the microfluidic devices. And mixing quality, as I was referring to, is the standardized concentration field, and can often be used to characterize the state of mixing. Now, we are going to come into another subtopic, which is heat transfer and micro heat exchangers. So, this is a very interesting application of microscale transport processes. Now, we all know that the Nusselt number, let us say, for flow through a tube, there are two distinct conditions. One is a constant heat flux and the other is a constant wall temperature. Now, in all cases, after the flow becomes fully developed, thermally fully developed, the Nusselt number defined as Hd by K, where D is the length scale by K is a constant, the value of which is 3.66 and 4 point something, depending on whether you have uniform heat flux condition or uniform wall temperature condition. Now, as we know that in microchannels, the value of D is quite small. So, if the value of D is small, then and if Nusselt number is constant, then the value of H has to increase. So, this is the reason that in microchannels, the value of heat transfer coefficient, convective heat transfer coefficient, can be very high. Okay. This fact or this phenomena of high convective heat transfer coefficient have been utilized in devising a number of equipments, devices, so to extract or to dissipate large quantities of heat from very small area. The examples that we can think of are for the cooling of microchips, where a small amount of heat may be generated, but the area where it is generated is very small. So, the heat flux that needs to be removed can be very large. So, a small amount of heat generation can lead to a situation where a large heat flux has to be removed in order to maintain the integrity of the device, integrity of the IC chip. And for some such situations, microscale heat exchangers based on or developed on the principle of high heat transfer coefficient can be a very effective tool to dissipate the large heat flux produced in such systems. So in this part of in this subtopic, we are going to look into the heat transfer in and micro heat exchangers. How do they perform? What are the governing equations for such cases, and so on. So we look into the fundamental heat transfer fundamentals, the energy balances, which we are very much familiar with. So for any control volume, the rate of energy in minus rate of energy out, and plus minus any kind of loss, generation, etc., all are rates, it's going to be equal to 0. So if we put into the first law of thermodynamics, then we need to add a dissipation function phi for closed systems, and for open systems these are the two equations for closed systems and for open systems, with phi denoting the dissipation term. So the dissipation phi takes into account the energy conservation from one form to another form accompanied by natural losses. For example, if we have flow in a microchannel with a bend, then the dissipation function over there essentially tells us it is related to the pressure losses in such a system and the frictional losses, which is going to change the internal energy content of the fluid. So these are dissipation functions, which could also be viscous losses, need to be added or need to be included in the energy equation so as to describe the energy content of the inflow of the inlet fluid and the outlet fluid, which are essentially all the fundamental relations, thermodynamic relations for energy balance. So let us say we have a process device where the mass flow rate is m, the heat flux q is over the boundary. So if it's a tube, then we can think of this q as the heat flux that is being added through the walls of the tube, and the technical work, which is Wt, or the mechanical power, which is denoted as the P, and there may be a chemical reaction, and therefore we can write the energy equation as given. So if you see here, the Q dot is the amount of heat, the amount of heat that is being the change in the energy, and this change in the energy has several components. So if you see the first term on the right hand side, so it's the net energy flowing to the control volume as a result of flow, as a result of convective flow, and and could be also as a result of conduction across the system boundaries. If you think of the second bracketed term on the right hand side, it refers to pressure. Okay. So m dot times delta P, that tells you the contribution of pressure to the overall measure of energy of a system. The third term on the right hand side tells us about the hydrodynamics, tells us about what is the head, the hydrodynamic head, which is being suppose the fluid is moving from low to high, then it's going to be its potential energy content. The fourth term on the right hand side refers to the kinetic energy, the change in kinetic energy of the flow. In alpha 1 and alpha 2 are the correction factors. So these are essentially the kinetic energy terms multiplied by the mass flow rate, and it tells us the change in kinetic energy between location 1 and location 2. The fourth term, E dot Q, is the energy produced or consumed. The energy produced can be a result of a reaction, so a chemical reaction. So it could be an exothermic or an endothermic reaction, and E dot Q simply takes into account the amount of energy produced or absorbed in such a system. And if you look at the last term, it's a technical work. It's the work that is being added to the system by a pump or extracted from the system by a turbine. So this equation then gives us the complete description of the net energy change, the spatial energy change for a flowing fluid, considering the internal energy, the kinetic energy, the potential energy, the work done against surface forces such as pressure, the heat generated due to, let's say, reactions, and the any amount of work that is being done on the system, for example a pump, or by the system, for example by a turbine. So such energy equation would be equally valid for microscale processes as well, with certain additional terms which we will see later on. So the energy of the fluid which flows in a straight line without chemical reactions, straight channel without chemical reactions and technical work, is simply the sum of the internal energy, the kinetic energy, and the gravitational energy. So we can add Fourier's law to it for conductive heat transfer perpendicular to the channel axis, and one can write the energy equation in the following form, which is simply going to be the time rate of change of internal and kinetic energy would be equal to the spatial change of this W is the mass flow rate, internal plus kinetic energy, then there would be a gravitational force component minus del Z of pressure times W minus del Z of K times del T del X. So this refers to the conductive heat which is being added to the system, minus del Z of tau times W. So tau times W, it gives us the dissipation plus W dot G, so any amount of work done. So this is the gravitational term, this is due to pressure, this is due to conduction, this is due to dissipation, and this is the amount of work that is being done by the system or on the system. So this can also be thought of as if it's the Bernoulli equation for the energy balance in channel flow, and can be simplified to suit each process. Now if we try to get a more meaningful equation to this, which is more common to us, we can write it as rho Cp dt by, so these are substantial derivatives, should be equal to epsilon plus divergence of K times gradient of T. So this is the conduction, and in here, since this is a substantial derivative, we have the time derivative. Since this is a substantial derivative, we have the time derivative as rho Cp del temperature over del time, plus we have Vx times del temperature over del x plus Vy times del temperature over del y, and so on. So this is the time dependent term, and this is the convection. So this refers to the convection, and this refers to conduction in a microchannel. So solving this equation essentially gives us the temperature distribution. If we could solve this problem, then it gives us the temperature distribution for any real process. Now heat conduction in small systems. So these are common for large systems as well as for small systems, but in small systems there would be a complicating factor, and the complicating factor is something that we need to be very careful about. For example, in Fourier's law, we all know about Fourier's law, which simply says that the heat flux is equal to minus K times delta T by delta X. Okay. So this Fourier's law assumes that the K, in this case, it assumes that the K, the thermal conductivity, is independent of position. It's same as in all directions. So there is no question of writing Kx, Ky, Kz, because all of them are equal and equal to one value of thermal conductivity. But so this is true for a bulk system. But when we think of a microsystem, the microsystem is the thermal conductivity, like many other physical property, is influenced by the microstructure of the material. So you have grain boundaries and crystal lattices which form additional resistances to heat transfer. And the solution of the three-dimensional heat conduction is often possible with numerical methods. So what you need to do then is the right form of Fourier's law would be the tensor nature, where the kx, ky, kz, etc. will be allowed to vary, and they are going to be functions of position. And the solution of this three-dimensional heat conduction equation is often possible only with numerical methods. So Fourier's equation of heat transfer has to be expanded to the tensor notation with the heat conductivity tensor. But that's one more thing that I would like to mention is that the miniaturization will not influence temperature development and the heat flux of a semi-infinite body. Now, what is the common form of semi-infinite body that we know of? Like the transient temperature development in a semi-infinite body is in one dimensional form is delta temperature by delta time is the alpha times del to t by del x square. So this equation needs to be solved where the temperature is a function of x as well as a function of time. So let's say we have a solid object where this is the x direction, and then what we need to have is then this is the constant temperature, this is the constant initial temperature T0 at time t equal to 0 for all values of x. So T0 is not a function of x and it's at time t equal to 0. Now when we allow this solid block to come in contact with another fluid whose temperature is lower than T0, then with time what you would see is that the temperature will fall. This is the temperature of the wall, and there would be a thermal boundary layer, a thin thermal boundary layer, and then the temperature will be equal to Tw. Okay. And this growth of this equation, the temperature variation can be expressed by this equation. And there are solutions for semi-infinite body, and which describes the temperature development in a solid body. So with constant wall temperature, Tw becomes constant, and the dimensionless temperature distribution is governed by an error function, which is an error function in t and x. So this t, which is a function of x and time, can be expressed by an error function. But what is important here to know is that the same equation can be used for semi-infinite body, and for small bodies there are certain numbers which we need to for small bodies which are small values of Biot number, and Biot number is defined as h d by k, where this k is the k of the solid, unlike Nusselt number which is also h d by k, but this k is for the liquid. So for a small value of Biot number, let's say we are talking about a sphere. Now in a sphere the diameter is small. Now if the diameter of the sphere is small, or if the value of k is large, then what one can think of is that the temperature inside the sphere will remain constant, will remain invariant with time, and this is the temperature T infinity, whereas this is the temperature of the solid. Now one can see that for small value of Biot number, that is small d or large Ks or small value of h, this Ts is going to be a function of time, but Ts is not going to be a function of let us say r in this case. So at one instant of time, this is going to be the temperature profile. At the next instance, the temperature will reduce to another value, but still inside the solid the temperature will not vary with R, and that is only possible if your Biot number value is small. And physically it tells us that if the thermal conductivity of the solid is large, if the size of the system is small, or if you are dealing with a small value of heat transfer coefficient, then the small value of Biot number indicate that I can assume space-wise isothermality in any solid. And once I assume space-wise isothermality, then this modeling that system becomes quite easy, and that is known as the lumped capacitance model. So, the lumped capacitance model, or LC model in short, allows us to get analytical solution of the temperature profile inside a solid object, and this is extremely useful. This is very useful to obtain the behavior of a fluid, behavior of a solid when it is quenched. So, let us say we have a very small steel ball, that hot steel ball which is put into a liquid, and how would the temperature of the steel ball change with time? That is extremely important from an engineering perspective. Similarly, for a microsystem, how does the temperature inside the microsystem vary with temperature? If we could assume that inside the small microsystem, since the length scale is small, there is no variation of temperature, then we would be able to obtain an analytic solution of temperature variation with time inside such a system. So, the two numbers of relevance here are Fourier number, which is alpha t by x square, where alpha is the thermal diffusivity, t is the time, x is the length scale, and Biot number as I have already explained. So, Fourier number tells us how fast a temperature front will penetrate into a solid, whereas in Biot number would tell us how the temperature of a solid is changing. So, these two are important parameters, the time dependent important parameters in the second Fourier law. Now, these are something, these I have already described partially, is that the total heat transfer in micro devices can consist of heat conduction through the walls and convective heat transfer from the wall into the fluid in the microchannel. So, for example, if you are making a micro device, and while you are making a micro device, if you consider only the convective heat losses from, let us say it's a tube and it's micro scale in size. So, the diameter of the tube is 100 micron and its length is 2 centimeters. So, now when you are it's made of silicon. Now, when it's, let us say, V-grooved micro heat pipe. Now, there are situations one has to consider not only convective heat losses from the outer wall of the microchannel, but the heat which gets transported through the wall. So, in micro devices, unlike in macro devices, the conduction heat transfer through the body of the device itself needs to be taken into account to calculate the total amount of heat loss or total amount of heat transfer from such a system. Secondly, as I said, for straight laminar flow, the dimensionless heat transfer coefficient is a constant and it is 4.3 or 3.66. For a wide gap or a narrow slit, the Nusselt number can vary for double-sided heat transfer, and for smaller channels, the heat transfer coefficient increases due to the constant Nusselt number, as I have already described. And at the entrance of a channel, at channel junctions, expansions, etc., the disturbed flow enhances the radial transport. So far we have seen that at the entrance of the channel or at a 90-degree bend, how the fluid dynamics gets altered, resulting in larger pressure drop. Here what we are saying is that not only the fluid dynamics gets altered, the altered fluid dynamics helps in transporting more heat due to the presence of the 90-degree bend. So an obstruction in the path or alteration of the fluid path not only increases pressure drop, it also increases heat transfer in microchannels. Microchannels. So, we get more pressure loss, but at the same time we have increased heat or mass transfer, and it is just a balance of which one we would want for our system. Okay. Now, one more thing is that okay, this is fine, but when we talk about Nusselt number, the constant value of Nusselt number and the smaller length scale giving rise to a high value of heat transfer coefficient, that is fine, but is it really beneficial? Is the high heat transfer rate helping us in obtaining a large heat removal? The answer is yes and no. The high heat transfer coefficient definitely helps us to extract more heat, but the area in consideration is quite small since we are talking about micro devices. So, we need to somehow increase the area of contact to utilize the full potential of a high heat transfer coefficient. Now, how that can be done? So, there has to be numerous tubes, micro tubes, which needs to be employed simultaneously to extract more heat. Now, whenever that happens, it gives rise, so it is a fabrication problem. How do we fabricate a large number of such channels which will utilize the high heat transfer coefficient, high convective heat transfer coefficient to extract more heat? And it is not only a fabrication issue, it is also an issue of how do we feed the coolant liquid equally into all such channels or tubes. So, proper feeding, uniform feeding of liquid through all the fabricated channels at the same time with minimal pressure drop, that is the major challenge being faced by engineers who are trying to build smaller and smaller devices to take the help of the higher convective heat transfer coefficient. Okay. We also know that when the flow starts taking place, it is not fully developed. It is not hydrodynamically fully developed or thermally fully developed. All the relations or correlations that we have so far are for fully developed flow, and for a micro device it may so happen that before the flow gets fully developed we reach end of the channel. Now, if that happens, then what is the equation, what is the relation to be used for calculating the Nusselt number, which is essentially a design parameter? So, the normal convention is to use the expression for Nusselt number for fully developed flow and multiply it with some factors in order to obtain the Nusselt number for the zone in which the flow is developing both thermally and hydrodynamically. So, for a large tube in a macro system, it is not a problem, because the entrance length part, the portion where the flow becomes fully developed, is quite small compared to the overall length of the channel. But in a micro channel, in a micro system, the length is so short that we may not provide enough length for the flow to become fully developed. So, we have these equations which tells us the Nusselt number. The Nusselt number which is developing is a Nusselt number which is a straight channel flow, and there are certain correlations which are available. So, this is the Prandtl number and this is the dimensionless length, and the equation is valid for the entire channel length x star and for Prandtl number greater than 0.1. So, since turbulent flow is rarely encountered in microchannels, so this kind of situation may not arise, but there are some turbulent conditions at locations especially near the bends and so on. Now comes the question of when we start reducing the size of the devices smaller and smaller and letting it operate at very low pressures. What happens is that we will probably reach a situation where we have struck the continuum limit. Now, when we we have continuum limit, and as we know that the continuum limit is generally expressed in terms of Knudsen number, which is the ratio of the mean free path and the characteristic length. So, if the value of Knudsen number is less than 10 to the power minus 2, that means the mean free path is small compared to the characteristic length, and for such cases the continuum and the thermodynamic equilibrium assumptions are appropriate, and the flow situations can be described by conventional no slip boundary condition. If the Knudsen number is in between the two, that is 10 to the power minus 2 to 10 to the power minus 1, then we come to the region which is known as the slip flow regime. So, in the slip flow regime, the Navier-Stokes equation will still remain valid provided we modify our no slip condition with a tangential slip velocity and a temperature jump incorporated into our boundary condition. So, we may not be able to use that u and v, the velocity in the x and the y component are both 0 at y equal to 0, where y equal to 0 denotes this wall, but we will have to provide a slip velocity, and there are several models which take into account the possibility of slip. Similar to slip velocity, we would also have to incorporate a temperature jump across the interface. So, previously for continuum cases, the temperature of the solid and the temperature of the liquid or the fluid adjacent to it are the same at the interface. But if the flow is rarefied, then we have a temperature jump across the interface. So, the reduced flow, that since we have a slip velocity, so therefore the flow resistance will be rather less, and the molecular motion etc., there is going to be insufficient momentum transfer between the wall and the bulk fluid. So, in order to characterize the amount of transfer, amount of momentum transfer and heat transfer, there is a concept called accommodation coefficient beta, which is defined as the ratio of the average energy which actually gets transferred between a surface and the gas molecule to the average energy which would theoretically be transferred if the impinging molecules reached complete equilibrium with the surface. Now, what happens here is that the molecule comes and hits the surface and reflects back into the bulk. Now, if this is a continuum case, then this should come, stay here for some time or stay here for sufficient amount of time to reach complete thermal equilibrium, and then will get reflected back. But due to the rarefied condition, it comes and then immediately it goes back. So, it cannot take enough the total amount of momentum, total quantity of momentum or total quantity of energy. So, this beta essentially tells us about what fraction of energy or what fraction of it can take due to the rarefied condition. So, for rarefied flow, the boundary condition, the velocity is going to be a function of zeta, which is called the slip length, and it can be this slip length can be calculated from the accommodation coefficient and the mean free path of the molecules. Okay. So, the experimental data on the accommodation coefficient beta, defines the efficiency of the momentum and energy transfer from molecules to the wall and vice versa. So, beta can be calculated from kinetic theory, and there are enough large quantity of data on beta which can be found in the literature. And similar to the slip, there is also a temperature jump across the wall, so that the temperature at x equal to 0 is not Tw, but G, which is a temperature jump coefficient like the coefficient zeta in the hydrodynamic case times the gradient at the wall. So, the temperature jump coefficient can be regarded as an additional distance to the gap. So, it may look something like this, that at the interface we have the temperature profile in the solid and the temperature profile in the fluid, but in the case of rarefied condition, we have the temperature profile in the solid and the temperature profile in the liquid, with a change in temperature on the solid side of the interface and on the liquid side of the interface. So, this is the temperature jump that we are talking about. So, we could think of a situation in which I am adding an additional resistance over here and this additional resistance is the temperature jump in rarefied gases for cases where Knudsen number is greater than 0.01. So, this temperature jump coefficient G, it can be regarded as an additional distance to the curve. So, for non-circular sections, in order to calculate these, half of the hydraulic diameter can be taken for Ra, and since we have more mobility of the molecules in rarefied condition, the Nusselt number for constant wall temperature is 5% higher than for the constant heat flux, and numerical study with Monte Carlo method indicated that slip flow model correctly represents convective heat transfer between the continuum and the molecular flow, and the influence of actual heat conduction must be considered, but the viscous heat dissipation and evaporative cooling and expansion cooling can be neglected for flows in microchannel. So, in summary, what we can say is that heat transfer in microchannel is essentially similar with most of the equations of macro scale that can be used, except for certain cases where for Fourier's law the thermal conductivity K needs to be the 3-dimensional variation of thermal conductivity has to be incorporated, and the tensor form of Fourier's law needs to be used with numerical solution. Only possibility is numerical solution. And secondly, during rarefied condition, the accommodation concept of accommodation coefficient tells us the efficiency of momentum transfer when a molecule hits a surface, and the accommodation coefficient, thermal accommodation coefficient, tells us that the impinging molecule and the wall has not reached complete thermal equilibrium, and this can be modeled by having the presence of a velocity at the wall where it's a slip, which is a function of the slip length and the gradient in velocity, and similarly the temperature can be expressed as a function of a temperature jump at the interface, which is as if we are adding a thin layer at the interface. So, these are some of the factors that need to be considered for modeling or for using convective flow, both the hydrodynamics and heat transfer in microchannels.